Right now, beneath North America, part of the continent's ancient foundation is slowly dripping into the Earth's mantle. This isn't a metaphor. Scientists built a detailed picture from hundreds of earthquakes recorded across roughly 6,000 seismic stations. What they found shows that even the deepest roots of continents aren't as eternal as they once seemed. These mantle drips move unimaginably slow, on the order of millions of years, so there is no immediate hazard. But over geologic time, this process can redirect volcanic activity, reshape mineral belts, and alter the stability of continents themselves. To understand why, we first need to look at what continents are resting on. The secret skeleton of continents. Beneath every stable continent lies something far stranger than most people imagine, a hidden skeleton of rock known as a Cratonic root. These are the ancient cores that keep continents steady, and geologists often compare them to the keel of ship. Just as a keel stabilizes a vessel in rough seas, these roots act as deep anchors, holding continental crust in place far above the shifting mantle. They are not shallow features. Most roots extend around 200 kilometers down, and in some regions they reach close to 350 kilometers. That depth places them in a mantle zone where rock slowly flows like taffy, yet Cratons still resist being worn away. The explanation lies in their chemistry. Billions of years ago, high-degree mantle melting stripped them of the unstable minerals that normally weaken rock. What remained was dense, dry, and rigid material that can withstand intense heat and pressure far better than ordinary crust can. Over Earth's history, these features became the foundation of the continents. Roughly 60% of today's continental lithosphere sits on top of Cratons. Their stability makes them among the oldest pieces of our planet. Some date back over 3 billion years, surviving countless cycles of ocean formation and destruction, mountain building, and supercontinents coming together and breaking apart. For a long time, that survival made them appear close to indestructible. People assumed that if a Craton had withstood billions of years of planetary upheaval, it might as well be permanent. And from a human perspective, they've always seemed like the most stable ground to build civilizations on, flat interiors of continents buffered from earthquakes and volcanism by those keels deep below. But permanence in geology is always relative. As tough as Cratons are, they exist in direct contact with the moving mantle beneath them. Over immense spans of time, those forces can strip sections of root away. The same structures that protect continents for eons carry within them the conditions for eventual failure. That's why, when scientists describe a root dripping into the mantle, it marks a profound shift. What looked unshakable is slowly vanishing into Earth's interior. And this raises a deeper puzzle. If even these buried skeletons can decay, then what does that mean for the supposed permanence of continents themselves? When eternal stones die. One of the clearest examples that Cratons can be dismantled comes from Eastern Asia. The North China Craton, once supported by a keel more than 200 kilometers thick, lost much of its lithospheric root during the Mesozoic. Studies of mantle fragments carried out by volcanic eruptions showed that this once rigid layer thinned dramatically from about 200 kilometers down to less than 80. That timing coincides with widespread volcanism across the region and the formation of rich mineral deposits, including major zones of gold. For geologists, this connection turned the case into more than a regional anomaly. It became the central evidence that Cratonic roots are not permanent and that their destruction leaves a lasting imprint at the surface. At first, it was not obvious how such a vast keel could disappear. But one fact quickly ruled out surface explanations. Erosion, rivers, glaciers, or atmosphere cannot bite into crust lying hundreds of kilometers below ground. The process had to come from deep mantle interactions. And in North China, the timing overlaps with one of the most powerful tectonic forces active on the planet at the time, the subduction of the Pacific Plate under East Asia. As that oceanic plate slid downward, it released fluids that weakened rocks above it and fueled hotter, more vigorous mantle motion beneath the Craton. Those same currents likely sheared away pieces of keel until the deep root was gone, replacing once rigid Cratonic mantle with hotter, weaker material. Evidence for this dismantling is found in two very different classes of rocks. Older volcanic xenoliths from before the root collapse contain minerals depleted in melt-producing elements, the hallmark of classic Cratonic mantle. Younger samples, however, erupted with much denser compositions typical of ordinary upper mantle. That turnover means the ancient keel had already disappeared by the time those magmas rose. Seismic imaging taken in more recent decades has reinforced the picture. The lithosphere beneath eastern North China today is less than half as thick as a Craton would require, with its base resting around 80 kilometers deep where once it extended more than 200. Combined, these records draw one of the most convincing portraits we have of root destruction in action. The consequences were profound. Without the buoyancy of its keel, the crust of eastern North China became weaker and more mobile. Faulting and extension reshaped its landscapes. Once quiet interiors became seismically active, and new volcanic fields opened routes for magma to reach the surface. Meanwhile, mineral-rich fluids released during the breakdown of the root supplied gold and other metals that we still mine today. The collapse removed stability, but also created resources, a reminder that Cratine death changes not just deep Earth structure, but the very surface on which societies later emerge. This episode forced geologists to rethink what a Cratine actually means. It is not the continent itself, but the buried skeleton that grants stability to the crust above. North China made it clear that removing that skeleton does not erase the continent. Instead, it changes the way that continent behaves. What was once a stable core became a zone of active tectonics, a place where volcanism proliferated and mineral wealth multiplied. In that light, Craton collapse is not only a destructive process, but a transformative one, reshaping entire regions for tens of millions of years after the root is gone. The broader implication was unavoidable. If North China's root could be stripped away, then no Craton is beyond risk. Their reputation as eternal is a matter of perspective. A billion years of survival is staggering to us, but not permanence to Earth. By linking xenolith chemistry, magmatism, mineral deposits, and seismic profiles, researchers built a complete case that Craton keels are not geological immortals, but features with lifespans and endpoints. That realization shifted the search elsewhere. If it happened here, could it also be happening beneath other continents today? Answering that question required a new kind of evidence. Geologists need to catch a Craton in the act of losing its root, not just reconstruct its disappearance millions of years later. Observing directly at depths of 200 kilometers was and remains impossible. No drill could reach that far. No borehole can withstand those pressures and temperatures. The challenge was finding a way to see into the mantle using signals that naturally cross it. Only then could scientists hope to compare a past case like North China with a present-day one still underway. And so the focus turned to Earth's natural probes, earthquakes, imaging the unimaginable. Studying what happens hundreds of kilometers underground is almost impossible with direct tools. No drill could ever reach so deep, and even if it could, material would collapse under crushing pressure and heat. Instead, researchers turned to waves moving through Earth itself. When an earthquake occurs, vibrations radiate outward. Those waves speed up through colder, rigid rock and slow down in hotter or weaker zones. By recording thousands of arrivals at surface stations, geophysicists can reconstruct a picture of the structures that shape the waves. It's like using ultrasound, sound waves returning as images, except on a planetary scale where the signals come not from a machine but from Earth's own tremors. The approach is called seismic tomography. What makes the latest effort remarkable is the precision of its methods. Instead of relying only on timing differences from one point to another, the team applied full waveform seismic tomography, which models the entire shape of the passing signal. Combined with a massive dataset, roughly 206 earthquakes recorded at about 6,000 seismic stations across North America, this strategy produced the clearest three-dimensional images of the deep lithosphere yet. Those maps trace structures stretching far into the mantle, well past the shallow crust and underlying keel, and in many cases extending downward toward the mantle transition zone, roughly 400 to 600 kilometers deep. That level of detail gave researchers their first direct look at how North America's Craton is behaving below the surface. The expectation was straightforward. A thick, solid keel should show up as a continuous block of unusually fast seismic velocities, the unmistakable footprint of cold, dense mantle lithosphere. Instead, the imaging revealed something very different. Parts of that keel appeared broken apart, rather than one uniform sheet. The tomography displayed drip-like blobs of high-velocity rock, detaching from the underside of the Craton and sagging down toward the transition zone. For decades, geologists suspected this process might be possible. They debated whether mantle flow could. slowly erode even the most chemically hardened roots, but until now their evidence came only from indirect clues like xenolith chemistry or volcanic eruptions. Here, for the first time, the process was captured mid-act. These detached shapes are not illusions or artifacts. Their seismic velocities confirm they are colder than the material they sink into. Imagine exactly what blocks of Cratonic root would look like if they were peeling away. The scale of motion is almost beyond human comprehension. The drips move at geologic pace, shifting millimeters to centimeters over a year, so to us they appear frozen in place. Yet on Earth's timescale, this is rapid. Over millions of years, entire portions of foundation can be displaced. What we see in the maps is essentially a time-still frame of a continent losing its anchor, instead of a static confirmation that roots can disappear. This is the first visual evidence of one actively unraveling. The work also highlights why tomography is such a powerful tool. Each earthquake wave takes a unique route, cutting across Earth's interior from a different angle. One path alone is like a single shadow, offering almost no depth. But stack thousands of such paths, waves crossing, bending, and scattering, and patterns emerge with enough definition to recover real structures. Thanks to computational advances, those thousands of records now combine into high-resolution models capable of distinguishing features less than 100 kilometers across. Without so many seismic stations operating in unison across a continent, the drips of North America's Craton would stay hidden. Equally important is that tomography makes these findings testable over time. Because the method relies on natural earthquakes, each new event can add a frame to the record. By returning to regions with updated data and recomputing the models, researchers can watch for changes in the lithosphere's anatomy. The potential to track long-term disintegration of continental roots means geologists may soon move from speculative cases to trend lines, noting how fast a keel fragments and whether pieces settle in the transition zone or keep sinking deeper into the lower mantle. Until recently, the destruction of Cratons was explained only in hindsight. Rocks at the surface carry whispers of vanished roots. Now, seismic tomography has shifted that picture from reconstruction to observation. Instead of only inferring that North China's root disappeared millions of years ago, we see North America's root deforming and dripping in the present. That revelation marks a turning point. For the first time, continental loss is observable as it unfolds, not only as an afterthought preserved in magma and minerals. Still, identifying the drips only raised a larger question. Why here? Why would one of Earth's great continental interiors, long thought to be among the most stable regions, suddenly begin shedding its foundation? The tomography maps provided the first suggestion. Alongside the sagging root fragments, they revealed an even larger anomaly running deep beneath the continent. And that is when the team began looking for a cause. What they uncovered pointed to something vast, still hidden below North America, a structure that outlived the ocean it once belonged to and continues to shape mantle circulation today. The phantom plate beneath our feet. What tomography uncovered beneath North America was not only the slow dripping of its cratonic root, but also the preserved remains of something far older, a vast oceanic plate that no longer exists at the surface. This was the Feralon plate, once spread across an ocean west of the continent. For millions of years it pushed eastward, diving under North America at the margin and sinking into the mantle. Surface rocks show little sign of it today. The ocean closed and the plate boundary vanished, but seismology paints a different picture. Clear fragments of the Feralon still lie deep within the Earth, lodged hundreds of kilometers down in the mantle transition zone and even parts of the lower mantle. It is a relic of an ancient ocean plate, now parked in the mantle and still tugging at the continent above. The Feralon was enormous, large enough to reshape half a continent during its descent. Its subduction fueled the rise of the Rocky Mountains and drove dramatic volcanic activity across western North America. Oceanic crust was scraped off and recycled into Earth's interior as the plate slid downward, while immense heat and pressure altered the geology above. Though the plate's surface expression has long disappeared, imaging shows that much of its body remains preserved deep within the planet, folded and warped but still intact. Instead of decaying quickly into the surrounding mantle, parts of it stalled in place, piling up and disrupting the flows of material nearby. Most subducted plates gradually warm and blend back into their surroundings after sinking. Over tens of millions of years, they lose their coherence, leaving the mantle more or less homogeneous again. The Feralon has not followed that usual pattern. Seismic studies reveal fragments lodged in the Mantle transition zone roughly 400 to 600 kilometers down, and others extending deeper into the lower mantle. Its position and immense size have made it behave less like a fleeting slab and more like a permanent feature, shaping mantle circulation itself. That unusual persistence matters because the very presence of such a slab changes how mantle currents move. Hot plumes trying to rise, or convection trying to circulate horizontally are diverted or blocked by its bulk. For the continent overhead, that means its stabilizing keel no longer floats in a calm environment, but instead is battered and stretched by redirected currents. Computer simulations of mantle circulation confirm this link. When researchers built models without the Feralon plate, the convection beneath North America flowed relatively smoothly, with the Cratonic root above remaining thick and buoyant over billions of years. But when the Feralon was included as a massive stalled slab, the scenario changed. Mantle flow became uneven, sweeping forcefully against the Craton's base. Infiltrating pockets of material further weakened the route. In every model case, dripping of the Cratonic keel occurred once the Feralon fragment was present. Remove the slab and the dripping disappears. Keep it in place and the root destabilizes. That direct comparison made the mechanism plain. The relic plate is not just a bystander, but the active driver of the ongoing disintegration. The presence of this slab explains why North America's Craton, long considered among the sturdiest on Earth, now shows evidence of breaking down. The Craton itself retains the chemical and structural traits that normally protect it from erosion. It is depleted, dense, and rigid. Yet combined with the massive forces of mantle circulation distorted by the Feralon, these traits cannot guarantee security. The slab continues to interfere with patterns of heat and flow, dragging, shearing, and weakening the base of the continental root. Rather than arising from the Craton itself, the instability originates externally as a consequence of plate tectonic history, stretching back more than 100 million years. This realization reframes how geologists understand continents. Subduction does not erase a plate completely. Parts of it may sink to depths beyond direct reach, but still remain intact for tens of millions of years. These buried remnants act like boulders in a river, reshaping everything around them. The Feralon is the clearest case study. Its preserved mass redirects mantle flow, releases fluids as it dehydrates, and introduces mechanical stresses in all directions. What tomography and modeling now show is that even the most resilient continent can be destabilized by inheriting such a neighbor underground. It also clarifies a puzzle that long bothered researchers. Earlier explanations for Craton destruction centered on local heating, stretching forces from above, or general mantle erosion. But none of those alone could fully explain the scale of root loss observed in places like North China, or the active dripping now unfolding beneath North America. Once the role of the Feralon was factored in, the patterns made sense. The slab does not cause dripping by itself, but by warping mantle flow and injecting fluids into once dry root, it sets the stage for portions of lithosphere to detach and sink. The models demonstrate that without its presence, stability would likely endure for far longer. With it, the root cannot remain intact indefinitely. From a human perspective, it's important to stress the timescale of these changes. The dripping we observe will play out over millions of years. People living on the continent will not notice sudden collapses or immediate hazards linked to this deep mantle activity. The significance here lies in understanding Earth's long-term evolution, not in predicting disasters within our lifetimes. Geological processes rarely move at speeds relevant to human society, and in this case, the researchers emphasize that once the slab fragments eventually sink deeper into the mantle, the destabilizing forces may ease. In other words, this is a long-term natural cycle, not an urgent threat. Still, the implications stretch beyond North America. If the fate of a Craton can hinge on the remnants of an ancient plate buried beneath it, then other so-called stable continents may also carry hidden vulnerabilities. Every continent has a tectonic history, written not only in surface rocks, but also in the slabs swallowed long ago and still preserved at depth. In North America's case, the Feralon provides a unique window into how past plate motions continue to dictate the present structure of the continent. Millions of years after the ocean had birthed, it has vanished. By combining seismic imaging with geodynamic models, scientists have built a coherent mechanism linking a buried plate to the ongoing dismantling of continental keel. It is a rare moment where evidence from multiple approaches converges on the same answer. The dripping of North America's Craton is not random or inevitable. It is a predictable consequence of a large, dense slab interfering with mantle circulation, dragging a continent into instability. That leaves us with an essential question. If mantle flow distorted by an ancient plate can destabilize the very base of a continent, what else contributes to those roots actually breaking apart and turning into drips? The tomography showed the connection, and the modeling confirmed the mechanical trigger. But understanding why pieces of Craton truly melt, weaken, and fall requires looking one step further into what happens when subducted plates deliver their hidden cargo to the mantle around them, the cocktail of destruction. The key to understanding why a Cratonic root starts to come apart lies in what geologists sometimes call the cocktail of destruction. On its own, the root is cold, stiff, and chemically depleted, traits that make it unusually resistant compared to the surrounding mantle. But once a subducted oceanic plate moves beneath it, the environment changes. Oceanic crust carries minerals packed with water, carbonates, and other volatiles. As the plate sinks into higher pressure and temperature, those minerals break down and release fluids into the mantle. When these fluids seep into the base of a Cratonic keel, they act like a solvent, lowering its melting point, softening its once rigid structure, and reintroducing elements that undo its buoyancy. Suddenly, a foundation that was designed to float becomes denser and easier to deform. At the same time, mantle circulation reshapes how forces act on the root. Subducted slabs do not simply slide down out of view. They reshape the flows around them. The Feralon plate, preserved beneath North America, redirects mantle currents in complex ways. Those currents bend and shear against the Craton's base, applying steady stress over immense spans of time. With fluids already weakened in the material, those flows no longer glance past harmlessly. They latch onto softened patches and pull them apart. Piece by piece, sections of the keel detach, separating into dense, irregular chunks that gravity draws downward. The outcome is not a clean fracture, but a slow peeling process, where each blob of lithosphere sags and sinks into the deeper mantle. Seismic tomography confirms the nature of these detached bodies. The images show anomalies that are modestly cooler by about 60 degrees Celsius than surround the mantle, which matches expectations for displaced continental material. Their composition appears enriched in Cratonic signatures, containing 20 to 50% more continental lithosphere than the mantle around them. These are not random mantle plumes. They are unmistakably pieces of the Craton itself stripped from below. Models estimate that in affected regions, this thinning has already removed between 20 and 60 kilometers of lithosphere. That may not sound dramatic compared to the root's overall thickness, but it represents a substantial loss of stabilizing mass over geological time. The combined sequence is simple. Fluids weaken, mantle flow pulls, and detached sections drip away. Neither factor on its own is sufficient. Fluids alone soften but do not detach, while flow alone pushes but cannot overcome the keel's rigidity. Together, they create the instability we now recognize in tomography. Each drip represents a cycle repeated over millions of years, steadily eroding what once seemed immovable. What makes this process remarkable is that it escapes notice at the surface. Standing on the continent above, nothing appears to change. The crust remains solid, landscapes continue their normal pace of uplift and erosion, and life goes on without disruption. Yet far below, volumes of rock comparable to entire mountain ranges quietly peel away and vanish into Earth's deeper layers. This is erosion running in reverse, not weather or rivers wearing down from above, but mantle circulation hollowing from below. And that raises the pressing question. If the root beneath North America is actively thinning, what consequences will arise for the continent sitting on top of it? Why it matters for North America. There is no danger that North America will suddenly lose stability at the surface. The changes happening deep underfoot operate over geological timescales, millions to tens of millions of years, far outside human experience. For life above, the crust remains firm and stable. But over Earth's long rhythms, the gradual thinning of the Cratonic root alters how the continent behaves. Losing that deep keel means the surface becomes more exposed to mantle influence, and that exposure has clear consequences. Volcanism can appear in unexpected places. Faults may shift into new activity. Basins can form as the land sinks unevenly.